Okay, let's begin. For today, we are going to solve problems, example problems for Thevenin and Norton equivalent circuits. Right? We saw the concept. We learned how to set up the problem. I went over the steps that you need to perform. Now we'll look at example problems and see how exactly we're going to solve for Thevenin and Norton equivalent circuits. So let's get to the right class first. 104. All right, example one. Determine the Thevenin equivalent resistance between terminals A and B. Okay, easing in slowly. Now, first thing I like to point out, if it says Thevenin resistance or whether it says Norton resistance, they mean exactly the same thing, right? If the question asks you to solve for Thevenin equivalent circuit, you still need to find the resistance. If it asks you to find the Norton equivalent circuit, you would still need to find the exact same resistance. And resistance is something that you have already done at the beginning of chapter 2, right? So RTH is the same as RN, no difference. Okay. Set up the problem correctly. That's the most important step. If you set it up correctly, then the analysis from that point on is relatively straightforward. So for RTH, what do we need to do? Well, first things first, it tells you to find the resistance between a specific pair of terminals. So that means you do not have to remove any component. You simply begin your analysis between those terminals. So what I will do is we'll first draw out all the resistors. We draw out all the resistors, and then we replace, or then we reduce all independent sources to 0. And RTH is, of course, between terminals A and B. So we reduce all independent sources to 0. Now, reducing an independent source to 0 this is a concept that we learned before superposition, right? Reducing independent sources to 0 means replacing the voltage sources with a short circuit and replacing the current sources with an open circuit. And so here at this point, if I remove the voltage source, it's going to be a short. That will be a short. The horizontal line, that will be a short, right? That's all we need to do. We don't need to do anything else. So you set it up correctly by drawing out the resistors, and then replacing the voltage sources with a short circuit. This is going to be a short, and the current sources are replaced with an open circuit. Now, you don't have to draw these out. You don't have to draw this out. I'm just drawing it for the purposes of explanation. Right? But makes sense, right? We want to find the total equivalent resistance between A and B. If we want to find the total REQ, well, we need to get rid of all the sources in the circuit. And we get rid of the sources by reducing them to 0. Reducing them to 0 means replacing voltage sources with a short and replacing current sources with an open. Once they're all gone, all we have left in the circuit are a bunch of resistors. All we do at that point is find REQ. To find REQ, we start at the farthest end from our analysis terminals. And in this case, it would simply be R1 in parallel with R2, which would be in series with R3, and then in parallel with R4. Make sense? Easy enough? Again, this equation is not as important as setting it up correctly. Once you set it up correctly, then this would automatically follow. Questions? Any questions at all?
Oh, this one basically I was going to just use like because it's like feminine like because it's in they are not terms and numbers, we will need to find anything else.
No. This is again something that we've already done at the beginning of this chapter, right? We solved a lot of problems trying to find REQ for resistors in series and parallel. So that's all it is. The setup is the most important part. Basically, you redraw the circuit and then you get the sources removed, right? And that's the most important part. Okay, example 2. Find the Thevenin and Norton circuits if the 2 ohm resistor represents the load resistance. What does that mean? It means this phrase is the same as this phrase. Means find the Thevenin circuit and the Norton circuit as seen by the 2 ohm resistor, right? As seen by the 2 ohm resistor. Right? 2 ohm resistor. So right at the beginning, we know that the 2 ohm resistor is not part of our analysis, right? We want to see how the circuit looks from the perspective of the 2 ohm resistor. This 2 ohm resistor could be like a large circuit that has a single equivalent Thevenin resistance of 2 ohms. We don't really care. We don't care what it is because it's not part of our analysis. Okay. So when we set up our circuits for the 3 quantities, we have to ignore that 2 ohm resistor. That is basically RL, load. It's a load resistance. It does not affect the circuit at all. So we need to find 3 quantities. You need to find RTH, VTH, and IN. Now, I always tell students, start with RTH because that's the simplest one. You solve that one first. It gives you some confidence that you can solve for the rest of the circuit also. Keep in mind, these 3 quantities are independent of each other. So the 3 circuits that you design for these 3 quantities are also independent of each other. They are 3 completely different circuits. The results that you find in one circuit has no bearing on the other 2 circuits. Okay. So let's start with RTH first. If we start with RTH and we draw the circuit for RTH, we set it up by drawing out the resistors first. The 2 ohm resistor is gone. The terminals are already marked as A and B. I'm going to keep those the same. And RTH. Voltage source, what do we do? Short it out. So we place a wire right there. That's it. Place a wire. This is 12 ohms, 4 ohms, and 6 ohms. Right? So RTH, again, I start at the farthest end. If I want to find RTH here, looking into these terminals, A and B, I start at the farthest end and I start reducing it towards the terminals. So the farthest end, I can see what can we say about the relationship between 12 and 6? Then parallel, right? They share 2 nodes each. It's connected at the top node, It's also connected at the bottom node because of that short, right? So 12 and 6 in parallel, and then that 12 and 6 parallel combination would be in series with a 4 ohm resistor. Does everyone see that? Right? You see enough? So RTH is 12 parallel 6 plus 4. 12 in parallel with 6, two resistors in parallel, product of the two divided by sum of the two. 12 times 6 is 72 divided by 18 gives us 4 plus 4. So 8 ohms. So RTH is equal to 8 ohms. Let's take a 10-second pause. Write it down, think over it. Let me know if you have any questions. Any questions at all? Yes.
We're finding the 7 resistance like that, where you said that 12 and 6 are in parallel.
Mhm.
Are we like starting from a certain point and working across the circuit?
Yes. So if we want to analyze from, between any pair of terminals, we always start at the farthest end and we start reducing it and move towards those terminals. You can also use the technique that I showed in class, which is drawing out two horizontal lines, A and B, and then drawing all the resistors vertically. And that would also help if it's a more complicated circuit. Any other questions? Okay, well, then let's move on to Thevenin voltage. At this point, you forget about the circuit for RTH. You forget about this value, again, because it has no bearing on the Thevenin voltage circuit. Then we have to redraw the circuit again, going back to the original. The original circuit looks like this. Right? 30 volts. What's my pin acting up? Hold on. Still not better. Okay. So this is what, 12 ohms? 12 ohms, 4 ohms, and 6. And 2 ohms is, of course, removed, right? It's not part of our analysis. So A, B, and we need to find the open circuit voltage, VOC, between these open terminals. Remember, it's the same circuit as the original one, except for those terminals removed. The component removed. Right? It asks us to find it as seen by 2 ohms. So we remove the 2 ohm resistor from the circuit. We draw the rest of the circuit as it is. You can see this circuit is different from the one for RTH. RTH should not have any sources at all. Whereas the Thevenin circuit, the Thevenin voltage circuit and the Norton current circuit should have all the sources back in it. So again, it's a different circuit. Forget about RTH, forget about the values. We simply have to analyze this circuit independently. So our job now is to find the open circuit voltage at the output terminals, and that open circuit voltage VOC would be our Thevenin voltage for that circuit up there. Does that make sense? I don't see a lot of nods in here. Okay, thank you. I need some feedback when I'm talking, otherwise I won't understand what's going on. So VOC, now here's an interesting concept. You can solve this using node voltage analysis, mesh current analysis. It's a one-step answer, basically. Okay, the analysis technique does not really matter. Superposition, of course, does not apply because you only have one source. But let me walk you through the concept. 30-volt source is supplying some current, right? So it's supplying some current. That current is flowing through the circuit. Let's call it I. Some current will go down here, 6 ohm. Is any current going to go through the 4 ohm resistor? Not at all, right? It's an open circuit. It's an open path. An open circuit, there's no pathway for the current to flow. So the 4 ohm resistor will not have any current. If it does not have any current, does it have any voltage across it? Again, no. So if it does not have any voltage across it, so here's the concept. If it does not have any voltage across it, means there is no difference in potential between the 2 points. Again, remember, voltage is nothing but the difference in electric potential between 2 points. If there is no current, there is no voltage, meaning there is no difference in electric potential. If there is no difference in electric potential, we are saying that the voltage at A is the same as this node right there. Did everyone follow the logic? 4 ohm is hanging in the air. There is no pathway for current to flow through. Since there is no pathway for current to flow through, voltage across 4 is 0. Since voltage across 4 is 0, means the two ends of that resistor are the exact same electric potential. They have the exact same voltage. So carrying that forward, if you want to find voltage at A with my reference at B, I need to find the voltage here, reference to B. And that just happens to be the voltage across the 6 ohm resistor. And so same potential, same voltage. Therefore, VAB is equal to VR6. Actually, it's not VR6. I'll just say V6. Does this make sense? Right? So that's the concept. Anytime you see a resistor that is not connected at one end, it may as well not be part of the circuit at all. And these 2 points would be the exact same potential. And this I can find simply by applying voltage division. Oh, so if it's not connected, if it's not part of the circuit, what can we say about the relationship between 12 and 6 ohms? In series, you're applying voltage to a series connection of resistors. What happens to the voltage? It gets divided. What technique comes to mind? Voltage division, one-step answer. So VOC is a fraction of 30 volts. The fraction is given by the resistor divided by total REQ, which would be 12 plus 6, 18. Gives me 10 volts. So my VTH is 10 volts. VTH is 10 volts. That makes sense. The analysis portion, again, you can use any tool at your disposal. You can use node voltage analysis, mesh current, superposition, KCL, KVL, Ohm's law, whatever you need, whatever tool you want, whatever tool you think is appropriate, you can use, right? It's the setup that's the most critical. If you perform the setup correctly, then the analysis is, again, analysis is not something that's new, right? And here, of course, is just the applying, the application of the concepts, fundamental concepts. All right, questions? Let's take a 10-second pause. Any questions at all? Yes.
Just have a confirmation. Is it VOD is mean, open circuit.
Open circuit voltage.
There is no current flow.
Yes. Yeah. 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 No current going through there. Again, there are a few campus passes missing from the website. So please go ahead and upload it as soon as you can. Now let's go to Norton. Once we finish analysis for Thevenin voltage, we forget about those results. We forget about that circuit. We go back to the original circuit. We redraw it again. Feels good to have my voice back. Everyone can hear me yelling. There's still some soreness, but much better than last week. All right. So 12 ohms, 4 ohms, and 6 ohms, 30 volts. So we redraw the same original circuit again. The 2 ohm resist, was it 2 ohm? Yeah, 2 ohm. The 2 ohm resistor at the load is removed, right? It's removed for all three circuits. But what else do we need to do to set this up correctly? We need a short, right? If we want to determine the Norton current for this circuit between the terminals A and B, I want to find the current flowing from A to B. It needs a pathway, so we place a short at the terminals. We place a short, and it is the short circuit current, ISC. That ISC gives us the Norton current, right? Norton current for the circuit. So we need to find ISC. And this circuit is again different from the circuit above, right? Your circuit changes every single time you make a change in the circuit. Even a short wire somewhere or an open circuit somewhere will render the circuit completely different. And so you need to analyze it independently of the other circuits that came before. Now, because of the short, what can we say about the relationship between 4 and 6 ohm resistors? In parallel, absolutely. I'm going to redraw the circuit in just a little different manner. So in the quiz, in the exam, when you're trying to solve circuits, you can redraw them as many times as you need until it starts making sense to you. In general, when you're trying to solve for circuits, redraw them as many times as you need. So here, what I'm going to do is this. This is 12. And then 4 and 6 are obviously in parallel. Because of the short, I can see if I trace the arrow back, it tells me that ISC is the same current that is flowing through the 4 ohm resistor, right? So all I need to do is find the current flowing through the 4 ohm resistor. To find the current in the 4 ohm resistor, I can take a couple of different techniques. They're kind of the same. The 4 and 6 in parallel would be what? 24 divided by 10, so 2.4 ohms, right? This is 2.4 ohms, this parallel connection, which should be in series with a 12 ohm resistor, right? This is 6 in parallel with 4. Which is 2.4. So all we need to do is apply voltage division and find the voltage across this resistor which is the voltage across 6 and 4 in parallel. Then apply Ohm's law again, find ISC. Make sense? Right? Well, let's do it. Hopefully it will make sense to everyone. So voltage across the 2.4 ohm resistor is going to be a fraction of 30 volts. The fraction is given by 2.4 divided by 14.4. This comes out to be, what is it? 2.4 divided by 14.4 into 30 comes out to be 5 volts. 5 volts. So the voltage across that resistor is 5 volts. Then the current through there is 5 divided by 4 ohms, the 1.25 amps. And therefore, my Norton current is 1.25 amps. Let's take a 20-second pause while you write it down, think over it. Let me know if you have any questions. Yeah. If you want to, but it'll be the same thing. You're simply applying like an equation around there and you get an equation and you'll get the answer directly. Mhm. No. No, the 2 ohm is at the beginning of the problem itself. It tells you that the 2 ohm resistor is the load resistor, so it's not part of any analysis. So you have to remove it completely from your analysis. It doesn't come into the picture at all. Yeah. No, we don't. We don't add the 2 ohm resistor at all. So in its place, we have a short circuit here. And when we set it up for the we simply open circuit. So we find the open circuit voltage for VTH, find the short circuit current right here. So 2 ohms doesn't come into the picture at all. And that's, again, keep harping on that for like every student. Setup is the most important part. Okay, setup is the most important. Now, if at the beginning of the problem, it stated terminals A and B, find the Thevenin circuit between terminals A and B, right? Then you don't need to remove anything. So if you go here, and it simply tells you, find the Thevenin circuit between the terminals A and B, then your 2 ohm resistor is part of your analysis. All 3 circuits. Does that make sense to everyone? Right? If the question simply states, find it between these terminals, then no modification necessary. You automatically begin your analysis between those terminals. If it says like this, that it's the load resistor or as seen by a particular component, then and then only do you remove that component from your analysis. And then for all 3 circuits, that 2 ohm is not there at all. That load resistor RL is not there at all. Okay. So again, setting up the problem is the most important. Once you set up the problem, the analysis can be any technique that you want. Any questions about Norton, Thevenin, resistance? Our final verification can be done using Ohm's law. You have IN times RTH. IN is 1.25. RTH is 8. The answer is 10 volts, which is actually equal to our VTH. So our answer is verified. Our answer is verified. That's going to be our absolute final step. So you mean the final Thevenin equivalent circuit, right? Yes. So we go back to the problem. This is our circuit, right? The final circuit or equivalent circuit to that is going to be this. Oh. My RTH was 8 ohms. My VTH was 10 volts. That is my final Thevenin circuit. Oh. Right? No, VTH. Sorry, my handwriting is worse than doctor's prescription. And final Norton circuit would be a current source in parallel with the resistor. The current source, of course, has a value of IN. IN was equal to 1.25 amps. And the resistor is still RTH or 8 ohms. This is terminal A, terminal B. This is where the 2 ohm resistor is connected back into the circuit. So we don't really care about the 2 ohm load resistor, right? That load could be anything we want. It does not affect our analysis at all. But now, if I asked you to apply voltage division and find the voltage across 2 ohms, or if I asked you to apply current division and find the current with 2 ohms, you can easily do so. If I change that 2 ohms to like 4 ohms, 40 ohms, 400 ohms, 568 ohms, doesn't really matter what value this resistor takes, you would still be able to find it in one step. And that's the beauty of Thevenin and Norton equivalent circuits. Yeah.
So it's also put RL in the strong or
That is RL. It doesn't matter what it is. It's RL, right? RL could be any value. Could be any value. So that again, this value did not affect our analysis at all. So could be any value. That is the load resistor RL. Yeah. Yes. It doesn't really matter. The point was that that's where it was disconnected from. They're connected, yeah. Again, if I was to ask, find the voltage, then I would say, yeah, join it together. There, it's now connected together. Okay, 15 minutes left. Let me get to example 3. This is going to be a little longer, so I will try to get through the setup as quickly as possible. So again, the same thing here. 17 ohm resistor represents the load. So we remove the 17 ohm resistor from our analysis. I'm going to begin with RTH. In RTH, I'm going to have 3 resistors. It's exactly the same as the previous one. RTH between terminals A and B. Voltage source is shorted out. Current source is opened. You have 5, 20, and 10. RTH is 5 in parallel with 20, in series with 10. 5 in parallel with 20 would give me 5 times 20 is 100 divided by 25, 4 ohms plus 10, 14 ohms. So let's make sure. Yeah, 14 ohms. Essentially, the resistive network is the same as the other one, except we now have a current source at the top. Okay, there's an additional current source at the top. Other than that, it's the same analysis, no difference. Now, for VTH and for IN, Thevenin voltage and Norton current, I want to solve for the open circuit voltage here, but there are two sources in there, so it's not a straightforward analysis. You can use mesh current, you can use node voltage, or you can use superposition. And what I'm going to do is I'm going to use superposition to find my Thevenin voltage. But first, let me set up the circuit correctly. So for Thevenin voltage, you redraw the original circuit. Everything is back in its place. Again, remember, you only remove the sources when you want to find the Thevenin resistance, not for anything else. So 5, 20, 10, and now you, of course, also have the current source, 1.5 amps. All right. Okay. You set up the problem, you set up the circuit to solve for VOC, Thevenin voltage. VOC is Thevenin voltage. So you set it up to solve Thevenin voltage. Now, at this point, you can apply mesh current analysis, node voltage analysis, or superposition. There are two sources, right? More than one source. So our usual techniques we cannot apply. So I'm going to choose superposition, and let's see. Not really. It's only two sources in there. I remember years ago when I first started solving this, I started off with, I think I started with like mesh current analysis, I believe, because there's only two meshes in here, like 1 and 2. It makes it easier to apply. But I specifically wanted to use superposition because I want to show something. So if you use mesh current analysis, there's only two meshes, right? 1 and 2 right there. Here, if you choose a mesh current going clockwise, you automatically have the answer, 1.5. Right? So mesh current in here is 1.5. So you only have one equation to write right there. And that's it. That's all you have to solve. Once you solve this, you can find the voltage there. But I want to use superposition. So I'm going to solve this using superposition. That means my VOC is going to be a combination of two. So let me, this is 30, no, this is 20 volts. I'm going to call this voltage source VS and current source IS. Okay, so my VOC has to be split in two parts. One would be VOC due to VS, the other one would be VOC due to IS. Both of them active one at a time. So if I choose VS active, I have to redraw the circuit again. It's the exact same circuit as the previous one. So the analysis also becomes the same. 5, 20, and 10. And this is VOC due to VS. And VOC due to VS comes out to be 20 times 20 divided by 25. Voltage division, right? 400 divided by 25 gives me, what does it give me? 16 volts. 16 volts. Right? Same analysis as the previous circuit, no difference. Then I'm going to say IS active. And if IS is active, voltage source is reduced to 0, means it's replaced with a short circuit. And this is interesting. You have a current source, you have A, you have B, and you have a resistor here. I want to find VOC due to IS. What can we say about the relationship between 5 and 20? They're in parallel, right? Because of the short right here, 5 and 20 are in parallel. So I reduce them to one single resistor. And then look, what I'm going to do is I'm going to take the circuit and I'm going to flip it on its side. Or I'm just going to redraw it on its side. So I have this current source, 10 ohm resistor in parallel with the current source. This resistor is 20 in parallel with 5. You can see it's not connected to anything. This is A, this is B. The same concept as before. Voltage at B is the same as the one on the left. And so VOC due to IS is 1.5 times 10. Well, let me write it out. 15 volts. 15 volts. Does that make sense? All I'm doing is I'm combining this and just drawing it a little bit differently so it makes sense, right? Two in parallel, there's no pathway for the current to flow through, so there is no voltage drop across here. All of the voltage is across 10 ohms. The polarity works itself out because the current source is flowing towards the right, upwards direction. It's coming from the top. That means this is plus, this is minus, matches up with our assumed polarity of VOC. Now, total VOC, job is not yet done. Total VOC is the sum of both. So it's 16 plus 15, 31 volts. Therefore, actual Thevenin voltage is 31 volts. Okay, actual Thevenin voltage is 31 volts. Now, I have 5 minutes left. I'm going to try to wrap up the Norton current in that time. If I'm unable to do so, I will continue. If you have to leave at 11, it's fine. You can leave. You can watch the video later for the remaining portion. Okay. So let's start with IN. IN is the same circuit again, but we have to set it up correctly. We have a current source. Oh, not plus. Let's do A and B. 5 ohms, 10 ohms, 20 ohms. And of course, current needs a pathway to flow through. So need to have a short circuit current going from A to B. This is 1.5 amps, right? 1.5 amps. So again, you can use mesh current analysis or node voltage analysis or superposition. Let's solve this using superposition again. Then I can say ISC is due to Vs, the voltage source, and ISC due to Is, the current source. So I have to redraw the circuit again. I'm going to redraw it for Vs active. Ohms, 5 ohms, 10 ohms. This would be ISC due to Vs. This is similar to example 1. In example 1, you had two resistors in parallel. 20 and 10 would be in parallel. I need to find the voltage across that parallel combination. If I find the voltage across the 20 and 10 in parallel combination, and then apply Ohm's law to find ISC Vs, right? So voltage across the 10 ohm resistor would be given by 20 volts into, let's see, 20 times 10 divided by 30. So 200 divided by 30, give me 6.67. So 6.67 divided by 11.67 gives me the voltage as 11.428. That is 20 and 10 in parallel. So .428 volts, and therefore ISC Vs would be V10 divided by 10, 1.1428 amps. When it's, sorry, moved a little bit further. When it's Is active, the voltage source is the short. ISC, 5 ohms, 20 ohms, and 10 ohms. Now, because the 5 and 20 are connected by the short, they are now in parallel. So 5 and 20 in parallel gives me 4 ohms. And because of the short on the right, ISC, I can redraw the circuit like this. ISC due to Is. And I can see there are two resistors in parallel. ISC due to Is is the current flowing through this parallel combination, right? It comes through here, gets divided into 10 ohms. It also goes through here into this parallel combination. So 5 and 20 are in parallel, 4 ohms, that ISC is going through that parallel combination. So I simply apply current division, and I can find ISC due to Is as a fraction of 1.5 divided by the Req. That Req is 10 in parallel with 4. 10 in parallel with 4 is 40 divided by 14, 2.857 divided by 4. Times 1.5, 1.071. And my total ISC is equal to 1.1428 plus 1.071 gives me 2.214. Therefore, my total Norton current is 2.214 amps. You verify this by using Ohm's law, IN times RTH, 2.214 times, what was my RTH? 14 ohms. And that should give me 30.9992, which is 31 volts, which is my VTH. And so my solution is correct and verified. And then, of course, the final 7-inch circuit. (17 ohms). RTH is 14 ohms. VTH is 31 volts. And my final Norton circuit is the current source IN, which is 2.214 amps in parallel with RTH, which is 14 ohms. Oh, come on, what's going on? (17 ohms). And that's it. That's a complete solution. Okay, so apologies for going over time. Those 3 examples take up a lot of time. If you have any questions, I'm available for a few more minutes, and I'll also be in my office later on. If you can't come into the office, send me an email. I'm happy to meet via Zoom. I'll say goodbye, and we'll see you all on Friday.